Our entire existence is hanging by a thread thinner than you can possibly imagine. If a single number woven into the fabric of empty space had come out even a fraction different, stars would never have ignited, atoms would never have clumped together, and nothing resembling a person capable of wondering about any of this would ever have existed. Physicists call this number the cosmological constant, and the closer you look at it, the stranger it becomes. Somewhere in the mathematics of the vacuum itself sits a value, almost unbelievably precise, that entire careers have been spent trying to explain why it isn't simply zero, or simply enormous, but instead sits on a razor's edge that happens to allow for galaxies, planets, chemistry, and us to understand why this number matters so much. You first have to unlearn something you were probably taught in school. The idea that empty space is actually empty. It isn't. When physicists strip away every particle, every photon, every last trace of matter from a region of space, something remains. The vacuum itself carries energy. This is not a philosophical flourish. It falls directly out of quantum field theory, one of the most rigorously tested frameworks in the history of science. Fields that permeate the universe, the same fields responsible for electrons, quarks, and light, never fully settle into stillness. Even in their lowest possible energy state, they flicker with what physicists call zero-point fluctuations, a residual jitter demanded by the uncertainty principle. Add up the energy of every quantum field, at every scale down to the smallest conceivable distance, and you get a number for the energy density of the vacuum. That number, translated into the language of general relativity, becomes the cosmological constant, usually written with the Greek letter lambda. This constant does something remarkable. Unlike the gravity from matter, which pulls things together, the energy of the vacuum pushes space apart. It acts like a kind of pressure baked into the geometry of the cosmos, and its effect grows stronger as the universe grows larger, because there is simply more empty space generating more of this outward push. The strange history of this idea actually begins with Albert Einstein himself, and with what he later called his greatest blunder, though history would eventually prove the blunder more prescient than he ever realized. When Einstein first applied his newly completed theory of general relativity to the universe as a whole in 1917, he ran into a problem. His equations, left alone, predicted a universe that could not remain static. Gravity, pulling on all the matter within it, should cause the cosmos to either expand or contract, and at the time, virtually every astronomer assumed the universe was fixed, eternal and unchanging on the largest scales, a quiet backdrop against which the stars simply sat in place. To force his equations to describe a static universe, Einstein inserted an additional term, a constant multiplied by the geometry of spacetime itself, precisely balanced to counteract the inward pull of gravity and hold everything still. He called it the cosmological constant. It was, in effect, the first appearance in physics of exactly the quantity that would later explain cosmic acceleration, though Einstein introduced it for the opposite purpose, not to accelerate the expansion of the universe, but to prevent any expansion from happening at all. Just over a decade later, the American astronomer Edwin Hubble, using the newly completed 100-inch telescope at Mount Wilson Observatory in California, made an observation that shattered the static universe assumption entirely. By carefully measuring the light from distant galaxies, Hubble found that nearly all of them were moving away from us, and that the farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, provided the first direct observational evidence that the universe was expanding, precisely the kind of behavior Einstein's original equations had predicted before he artificially forced them into stillness. Einstein is said to have referred to his invented cosmological constant as his biggest blunder once he learned of Hubble's results, since the term now appeared entirely unnecessary for much of the rest of the 20th century. The cosmological constant became something of a historical footnote, a mathematical patch introduced to solve a problem that observation had since rendered obsolete, occasionally revived by theorists exploring the outer edges of cosmological models, but rarely treated as a serious feature of physical reality. For most of the 20th century, scientists assumed this term in Einstein's equations was either exactly zero or so close to it that it made no observable difference. Then, in the late 1990s, two independent teams of astronomers, one led by Saul Perlmutter and another by Schmidt and Adam Riess, set out to measure how fast the expansion of the universe was slowing down. They were using exploding stars called Type 1a supernova as cosmic mile markers, objects with a known intrinsic brightness that let astronomers calculate precise distances across billions of light years. The assumption going in was straightforward. Gravity from all the matter in the universe should be gradually breaking the expansion, the same way tossing a ball into the air causes it to slow as gravity pulls it back down. What they found instead appended modern cosmology. The most distant supernova were fainter than they should have been if the expansion were merely coasting or slowing. They were farther away than expected, which meant the expansion of the universe was not decelerating at all. It was speeding up. Something was actively pushing galaxies apart from one another at an accelerating rate, and the leading candidate to explain this was precisely the energy density of empty space. The cosmological constant, now rebranded in the popular imagination as dark energy. This discovery earned Perlmutter, Schmidt, and Riess the Nobel Prize in Physics in 2011, and it forced physicists to take seriously a term in Einstein's equations they had spent decades trying to ignore. What made the results so difficult to dismiss was the sheer care both teams took to rule out mundane explanations. Could interstellar dust be dimming the light from distant supernova in a way that mimicked greater distance? Could the supernova themselves have been systematically different, intrinsically fainter, in the ancient, chemically simpler universe of billions of years ago compared to nearby, more recent examples? Both research groups tested these possibilities, cross-checking their results against each other using independent telescopes, independent data reduction techniques, and independent statistical methods, precisely because a claim this extraordinary demanded an extraordinary standard of evidence. When both groups converged on the same conclusion, despite working somewhat competitively and independently, the case for cosmic acceleration became difficult to explain away as a systematic error or a statistical fluke. Subsequent, entirely independent lines of evidence have since reinforced the conclusion many times over. Detailed measurements of the cosmic microwave background by satellites such as the Wilkinson Microwave Anisotropy probe and later the European Space Agency's Planck satellite, along with large-scale surveys mapping how galaxies cluster together across cosmic history, have all pointed toward the same underlying picture: a universe in which roughly 68% of all the energy content is bound up in this mysterious dark energy, with the remainder split between ordinary matter and the invisible scaffolding of dark matter that helps hold galaxies together. Here is where the story turns from strange to almost impossible to believe. If you calculate the expected energy density of the vacuum using quantum field theory, summing the contributions from every known field at every energy scale physics currently understands, you get an answer. But that answer is not just a little off from what astronomers actually observe. It is off by a factor of roughly 10 to the power of 120. Try to picture that number. It is a 1 followed by 120 zeros. It dwarfs the number of atoms in the observable universe, which is itself only around 10 to the power of 80. Physicists have called this mismatch the worst prediction in the history of science, and they are not exaggerating for effect. No other calculation in any field comes anywhere close to being this wrong when checked against measurement. If that theoretical prediction were actually correct, the consequences would be immediate and catastrophic. A vacuum energy density that enormous would generate a repulsive force so overwhelming that space itself would have torn apart. Within a fraction of a second after the Big Bang, matter would never have had the chance to clump into atoms, let alone stars or galaxies. The universe would have inflated into an unrecognizable, diffuse nothing before the first proton ever formed. And yet here we are, on a rocky planet orbiting an ordinary star, embedded in a galaxy that took billions of years to assemble, surrounded by billions of other galaxies doing the same thing. Reality plainly did not follow the quantum field theory prediction. The actual value of the cosmological constant is almost inconceivably small, but not exactly zero. It sits at a value that permits slow, patient, billion-year processes like star formation and galactic assembly to unfold, while still allowing space to accelerate its expansion once those structures are already largely in place. This is the razor's edge people talk about when they describe cosmic fine-tuning. Nudge the constant up by even a modest amount relative to its actual value, and the accelerating expansion would have kicked in early enough to fling matter apart before gravity could pull it into stars and galaxies at all. Nudge it the other way, into negative territory, and the universe would eventually stop expanding and collapse back on itself. A big crunch instead of the long, cold future we are apparently heading toward. The window of values compatible with a universe that contains complex structure, chemistry, and observers turns out to be staggeringly narrow compared to the full range of values the mathematics of quantum field theory would naively allow. Modern instruments are now measuring the consequences of this constant with a precision that would have seemed like science fiction to Perlmutter and Schmidt's generation. The Euclid Space Telescope, launched by the European Space Agency, is mapping the shapes and positions of billions of galaxies across more than a third of the sky, tracing how the large-scale structure of the cosmos has evolved as dark energy has done its slow work of stretching space apart. Alongside it, NASA's Nancy Grace Roman Space Telescope is being prepared to survey vast swaths of sky with a field of view roughly 100 times larger than the Hubble Space Telescope, hunting for the subtle statistical fingerprints that dark energy leaves on the distribution of galaxies and the bending of light around massive structures, a phenomenon called weak gravitational lensing. Together, these observatories are trying to answer a question that sounds almost absurdly simple but turns out to be one of the deepest in physics. Is the number driving cosmic acceleration truly constant, unchanging across the history of the universe, or has it been quietly shifting all along? Euclid, which launched in July of 2023 and began its main survey operations soon after, is designed to observe roughly 1.5 billion galaxies over its 6-year mission, reconstructing a three-dimensional map of cosmic structure stretching back some 10 billion years into the universe's history. It does this partly by measuring weak gravitational lensing, the subtle way the mass of intervening galaxies and dark matter bends and distorts the light of more distant galaxies behind them. A distortion so slight for any individual galaxy that it can only be detected statistically by averaging the shapes of millions of galaxies across the sky. Euclid also tracks baryon acoustic oscillations, faint ripples in the density of matter left over from sound waves that propagated through the hot plasma of the early universe before recombination. Ripples whose characteristic size acts as a kind of cosmic ruler, allowing astronomers to measure distances across the universe with remarkable precision. By comparing how this ruler's apparent size changes at different distances, and therefore at different points in cosmic history, scientists can reconstruct exactly how the expansion rate of the universe has evolved over time, which is precisely the kind of measurement needed to determine whether dark energy has remained constant or has shifted in strength. The Nancy Grace Roman Space Telescope, expected to begin science operations in the latter half of this decade, will complement Euclid's survey using a different but related approach, employing the same basic mirror size as the Hubble Space Telescope but paired with a much wider field of view, allowing it to survey vast areas of sky far more efficiently. Roman will conduct its own weak lensing and baryon acoustic oscillation surveys, while also observing thousands of distant Type 1a supernova with enough precision to trace the expansion history of the universe across a wide range of cosmic epochs, providing an independent check on Euclid's results using different instruments, different systematic effects, and different observational strategies. Exactly the kind of redundancy that gives scientists confidence when two entirely separate methods converge on the same answer. Alongside these dedicated dark energy missions, the James Webb Space Telescope, though not built primarily to study dark energy, has already begun contributing unexpected pieces to this puzzle. Since beginning science operations in 2022, Webb has detected surprisingly massive, surprisingly well-formed galaxies at redshifts corresponding to a universe only a few 100 million years old, earlier and more developed than many models of galaxy formation had predicted. These early results are still being actively debated within the astronomical community, with researchers checking whether the apparent masses of these ancient galaxies have been correctly measured, and whether current models of how quickly gas can collapse into stars in the early universe need revision. Whatever the ultimate resolution, these observations are a reminder that the story of how matter organized itself in the young universe, precisely the process the cosmological constant had to leave enough room for, is still being actively rewritten as new data arrives, sometimes in surprising directions nobody fully anticipated. Before going further, it's worth pausing to actually picture the alternative universe these missions are testing against. Imagine a cosmos where the vacuum energy had been just slightly stronger. In that reality, the accelerating expansion would have overwhelmed gravity almost immediately after the hot, dense early universe began to cool. Clouds of hydrogen and helium, the raw material for every star that has ever burned, would have been stretched apart faster than gravity could pull them together. No stellar nurseries, no fusion reactions lighting up the darkness, no forges capable of building the heavier elements woven into rock, water, and living tissue. Now imagine the opposite, a universe where the constant were negative and large, enough in magnitude to halt the expansion outright. Gravity would have eventually won the tug-of-war entirely, pulling everything back into a searing, dense collapse. A mirror image of the Big Bang running in reverse, likely well before life of any kind had a chance to emerge. Neither of these alternate universes would ever produce someone capable of standing on a planet's surface asking why the numbers came out the way they did. If you want to actually see how directly the story connects to your own night sky, it helps to search for images of the deepest surveys astronomers have produced: the Hubble Deep Field, the James Webb images of galaxy clusters bending light from objects behind them. Every one of those pinpricks of light is a testament to a universe where matter had just enough time and just the right conditions to organize itself into galaxies before the expansion of space pulled everything apart. If you have not seen those images before, it is worth taking a moment to look them up, because they make the abstract mathematics of fine-tuning feel suddenly, vividly real. So why does the raw quantum field theory calculation come out so catastrophically wrong. This is where physics starts to feel less like settled science and more like an unsolved detective story. One idea involves supersymmetry, a proposed extension of the standard model of particle physics, in which every known particle has a heavier particle in a perfectly supersymmetric universe. The vacuum energy contributions from ordinary particles and their supersymmetric partners would cancel each other out almost exactly, because bosons and fermions contribute with opposite signs to the total. The trouble is that supersymmetry, if it exists at all, must be broken in our universe, since we have never detected any of these partner particles despite years of searching at facilities like the Large Hadron Collider, and even accounting for that symmetry breaking. Calculations still leave a discrepancy of around 60 orders of magnitude, an improvement, but nowhere close to solving the problem outright. Other physicists have proposed modifications to general relativity itself, frameworks in which gravity behaves differently on the largest cosmic scales in ways that could suppress the effective contribution of vacuum energy, without requiring it to cancel through some hidden symmetry. These models are active areas of research, but so far none of them has produced a testable prediction sharp enough to definitively distinguish itself from the standard picture, nor from its many competitors. The honest scientific answer, as unsatisfying as it might feel, is that nobody currently has a complete, verified explanation for why the vacuum energy density is as small as it is while still being not. This gap between prediction and observation remains one of the most significant open problems in all of theoretical physics, and it is a genuinely humbling reminder of how much remains unknown even within a framework as successful as the standard model now. Step back from the equations for a moment and think about what this constant actually had to accomplish for a universe like ours to exist at all. It is not enough for space to merely avoid tearing itself apart. The particular value of the cosmological constant also had to leave room, in cosmic terms, for a very specific and delicate sequence of events: hot, ionized plasma cooling down enough for neutral hydrogen atoms to form, gravity slowly gathering that hydrogen into the first clumps of matter, and those clumps eventually growing dense enough to ignite nuclear fusion in the cores of the first stars. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms, an event cosmologists call recombination. Before that moment, the universe was an opaque plasma, and light could not travel freely because it kept scattering off free electrons. The moment recombination happened, photons were released to stream across the cosmos essentially unimpeded, and we can still detect the faint afterglow of that release today as the cosmic microwave background, a nearly uniform bath of radiation with a temperature of about 2.7 degrees above absolute zero. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, who initially thought the persistent background noise in their radio antenna was caused by pigeon droppings. Once neutral hydrogen filled the universe, gravity had a delicate job to do. The cosmological constant had to be small enough and slow-acting enough on early timescales that it did not disrupt the gradual gravitational clumping of that hydrogen into denser and denser regions over hundreds of millions of years. Tiny fluctuations in density, seeded during an even earlier period called cosmic inflation, acted like gravitational wells that hydrogen gas slowly funneled into. Over time, these regions grew dense enough and hot enough at their cores for hydrogen nuclei to fuse into helium, releasing the burst of energy that we recognize as starlight. The very first generation of stars, sometimes called population 3 stars, are thought to have been enormous, hundreds of times the mass of our Sun, composed of nothing but hydrogen and helium because no heavier elements yet existed anywhere in the universe. before the first stars ever formed. The young universe had already run through one earlier chapter of element building, a much simpler one that set the raw ingredients everything afterward would depend on. In the first few minutes after the Big Bang, when the universe was still hot and dense enough for nuclear reactions to occur freely throughout all of space, protons and neutrons fused together in a brief window known as Big Bang nucleosynthesis. This process produced hydrogen, the overwhelming majority of the universe's normal matter, along with helium making up roughly a quarter of the total mass of ordinary matter, and only trace amounts of lithium and a few other light isotopes. It could not go any further than that. The universe expanded and cooled too quickly for heavier elements to form through this early process, and the reactions shut off within about 20 minutes. This left the cosmos filled almost entirely with the two simplest elements on the periodic table, waiting patiently, sometimes for hundreds of millions of years, for gravity to gather them into the first stars capable of finishing the job that the Big Bang itself could not. This is the point where the story of fine-tuning stops being just about space and starts being directly about you. Every element heavier than helium, everything from the carbon in your cells to the oxygen you're breathing to the calcium in your bones, was forged inside the nuclear furnace of a star, or in the cataclysmic explosion of a star's death. Carbon, in particular, required an almost improbable nuclear coincidence to form in any meaningful quantity at all. A process called the triple-alpha reaction, in which 3 helium nuclei fuse together inside a star's core. The physicist Fred Hoyle realized in the 1950s that this reaction should be far too rare to account for the abundance of carbon actually observed in the universe, unless there existed a specific excited energy state of the carbon nucleus that dramatically boosted the reaction's probability, a state that had not yet been detected. Hoyle predicted its existence purely from the argument that carbon-based life obviously existed to make the observation in the first place, and laboratory experiments soon confirmed he was right. That resonance is now called the Hoyle state, and it stands as one of the earliest and most striking examples of scientists using the simple facts of our own existence to make a testable prediction about nuclear physics. None of this stellar alchemy could have happened if the cosmological constant had been tuned even slightly differently. Too large, and the accelerating expansion would have shredded the gas clouds before gravity ever assembled the first stars. Too negative, and the universe might have recollapsed before those stars had time to live out their multi-million or multi-billion year lifespans and seed the cosmos with heavier elements through supernova explosions. It is worth remembering, before going further, that the periodic table hanging on classroom walls around the world is not some inevitable feature of physics. It is the product of a chain of coincidences and requirements stretching from the precise density of vacuum energy all the way down to a specific excited state in a carbon nucleus. And every step in that chain had to land within an extremely narrow range of possible outcomes. Carbon was only the beginning of that chain. Once a massive star has spent its supply of hydrogen and then helium, gravity compresses its core further, driving temperatures high enough to fuse carbon into neon, neon into oxygen and magnesium, and so on up through the periodic table in a series of increasingly rapid nuclear burning stages, each one lasting a shorter span of time than the one before it. A star many times the mass of the sun might burn hydrogen for millions of years, helium for a few 100,000, and then race through its final stages of silicon burning in a matter of days before its core collapses. This entire elegant, layered structure, sometimes described by astronomers using the image of an onion, with successive shells of different elements fusing at different depths, builds elements up to iron. the point at which fusion stops releasing energy and starts consuming it instead. Elements heavier than iron, including the gold, silver, and platinum found in jewelry, the iodine your thyroid depends on, and many of the heavier elements essential to biology and technology alike require a different, far more violent origin. That origin arrives in the form of a star's death. When a massive star exhausts its nuclear fuel entirely, its iron core can no longer support itself against the crushing weight of gravity, and it collapses in a fraction of a second, triggering a supernova explosion so powerful that, briefly, a single dying star can outshine its entire host galaxy. Within the extreme densities and neutron-rich conditions of that explosion, and in the aftermath of the even more extreme events, astronomers have since confirmed collisions between two neutron stars. Atomic nuclei can rapidly capture neutrons faster than they can decay, building up into heavy, often unstable isotopes that later decay into the stable heavy elements found scattered across the periodic table. In 2017, astronomers observed gravitational waves from precisely such a neutron-star collision, an event known as GW 170817, and were able to follow up with telescopes across the electromagnetic spectrum, directly confirming that this kind of collision produces significant quantities of heavy elements including gold and platinum, spraying them outward into interstellar space where they eventually become incorporated into new generations of stars, planets, and, on at least one known occasion, the periodic table memorized in a chemistry classroom. All of this, the layered burning inside a star, the supernova explosion, the neutron-star collision, ultimately depends on stars existing long enough and in large enough numbers for these processes to unfold across cosmic history, and that requirement leads directly back to the cosmological constant, because the value of that constant governs how much time the universe had and how densely matter was able to gather. Before cosmic acceleration began pulling everything apart on the largest scales, every gold ring, every strand of DNA built partly from phosphorus, every red blood cell relying on iron to carry oxygen, exists because the vacuum energy of the universe happened to be small enough for long enough to allow this multi-billion-year chain of stellar deaths and rebirths to run its course. If you find this kind of thing as strange and compelling as I do, it's worth taking a moment now to like this video and subscribe, because we're about to go even deeper into the philosophical debate this fine-tuning has ignited among physicists, cosmologists, and philosophers alike, a debate that gets stranger and more contested the further you follow it. So who, or what, set the dial on this number in the first place? This is where the science gives way, at least partially, to a genuine and ongoing philosophical dispute, one that scientists themselves disagree about openly and often passionately. There are, broadly speaking, several major camps trying to make sense of why the cosmological constant sits where it does. The first possibility is that we are simply missing a piece of physics, some deeper theory that, once discovered, would show that the value of the cosmological constant is not arbitrary at all, but mathematically forced to be exactly what we observe. The same way the charge of the electron or the mass of the proton falls out of deeper physical principles rather than being a free dial that could have been set to anything. Proponents of this view point to the long history of physics resolving apparent coincidences through deeper theory. The precise ratios of orbital periods among moons of Jupiter once looked like a strange numerical coincidence until scientists understood the underlying dynamics of orbital resonance. Many physicists hope that a future theory of quantum gravity, something that successfully unifies general relativity with quantum mechanics, a unification that has eluded physicists since Einstein's own era, might eventually explain the cosmological constant as a necessary, consequence of the universe's underlying structure rather than an unexplained accident. The second major idea is the anthropic principle, and it deserves to be explained carefully because it is frequently misunderstood or caricatured, sometimes even by scientists arguing against it. The anthropic principle, in its most defensible form, is not a claim that the universe was designed with observers in mind. It is a statement about selection bias. If a wide range of values for the cosmological constant and other fundamental parameters are physically possible, whether in a single universe with different initial conditions elsewhere, or across a genuine multiplicity of separate universes, then the only versions of that landscape any observer could ever actually find themselves in are the ones capable of producing observers at all. In other words, we should not be surprised to measure a value of the cosmological constant compatible with our own existence, because measuring any other value would require the presence of someone to make the measurement, and by definition, a universe hostile to structure and chemistry cannot produce anyone to notice. This is a genuinely subtle point, and it's easy to get it wrong in either direction. The anthropic principle does not explain why the cosmological constant has a small non-zero value instead of being exactly zero, and it does not explain why the specific mechanism generating vacuum energy behaves the way it does at a fundamental level. What it explains is why we, as observers who exist to ask the question, would only ever find ourselves measuring a value compatible with our own existence, out of whatever broader range of values might be possible somewhere in a larger cosmic landscape. Critics of the anthropic approach argue that it risks becoming a science-stopping move, a way of declaring a mystery solved by appealing to our own presence rather than digging for the underlying physical mechanism. Proponents counter that it is simply honest statistical reasoning applied to a genuinely unusual observational situation, no more mysterious in principle than noting that a person who has just survived a plane crash should not be shocked to find themselves alive to reflect on it, since anyone who did not survive would not be doing any reflecting. The anthropic argument only becomes a full explanation, rather than just an observation about selection bias. If there is actually some underlying mechanism that generates many different regions or universes with different values of the cosmological constant in the first place, a distribution to select from, and that leads directly into one of the most contested ideas in modern theoretical physics. It's also worth noting that the anthropic debate is not simply a divide between physicists and philosophers standing on opposite sides of a fence. It runs directly through the community of working cosmologists themselves. The physicist Leonard Susskind, one of the pioneers of string theory, has argued that the anthropic principle, combined with the string landscape, represents a legitimate and perhaps unavoidable shift in how physics explains certain fundamental parameters, a genuine departure from the older hope that every constant in nature would eventually be derived from first principles with a single, unique value. Other prominent physicists, including Lee Smolin, have pushed back forcefully, arguing that leaning on anthropic reasoning risks abandoning the deeper explanatory ambitions that have historically driven physics forward, and have proposed alternative frameworks, such as Smolin's own speculative idea of cosmological natural selection, in which universes might somehow give rise to other universes through processes analogous to biological reproduction inside black holes, with the physical constants of the offspring universe varying slightly from those of the parent. A framework that would allow for something like evolutionary selection towards certain ranges of values over cosmic generations, entirely independent of any observer's existence. This idea remains speculative and has not gained wide acceptance, but it illustrates just how many genuinely different directions serious physicists have explored trying to explain a single number. before reaching that idea. Though, it's important to bring the story up to the present moment, because the ground here has genuinely started shifting in recent years. And this is not a settled textbook chapter, but an active, unresolved area of research. For decades, the working assumption in cosmology was that dark energy behaves exactly like Einstein's cosmological constant, a fixed, unchanging energy density that never varies across cosmic history. That assumption underpins the standard model of cosmology, known as lambda-cold dark matter, or lambda-CT, which has successfully explained an enormous range of observations, from the pattern of the cosmic microwave background to the large-scale distribution of galaxies. But the Dark Energy Spectroscopic Instrument, an ambitious survey mounted on the Mayall Telescope in Arizona and involving more than 900 researchers from over 70 institutions worldwide, has spent the past several years constructing the largest three-dimensional map of the universe ever built, tracking how matter has clustered together over roughly the last 11 billion years of cosmic history. When the collaboration released its first year of results in 2024, they reported something unexpected, hints that the strength of dark energy might not be constant after all, that it could be weakening slightly over cosmic time rather than holding perfectly steady. Taken entirely on its own, the DESI data remained broadly consistent with the standard lambda CDM picture. But when combined with independent measurements, including the cosmic microwave background, distant supernova, and the subtle gravitational lensing of light from faraway galaxies, the statistical preference for a dark energy that evolves over time rather than staying fixed grew stronger by the time DESI released its second major batch of results. Drawing on 3 years of survey data, that preference for an evolving dark energy over the simple, unchanging cosmological constant had strengthened to somewhere between roughly 3 and 4 standard deviations, depending on exactly which combination of datasets researchers used in the analysis. In the world of physics, a 5 standard deviation result is typically the threshold required before something is declared a confirmed discovery. So this evidence, while provocative and genuinely exciting to the cosmology community, is not yet considered definitive. Some researchers analyzing the same data have pushed back, arguing that subtle disagreements between how different types of measurements are combined, particularly between the DESI baryon acoustic oscillation data and various supernova catalogs, could be inflating the apparent signal, and that the case for evolving dark energy may be less secure than the headline statistics suggest. Other independent analyses have reached the opposite conclusion, finding the preference for dynamical dark energy persists even when each dataset is examined on its own. What makes this genuinely thrilling, rather than simply confusing, is what it would mean if the evolving dark energy interpretation eventually holds up under further scrutiny. If dark energy is not a true constant, then it cannot be the fixed vacuum energy density predicted, however catastrophically incorrectly, by quantum field theory. It would instead point toward something more like a dynamical field, sometimes called quintessence in the scientific literature, a field that can change in strength over the history of the universe, the way other fields in physics evolve and shift under changing conditions. Confirming this would not resolve the vacuum catastrophe outright, but it would fundamentally reshape the question, redirecting decades of theoretical effort away from explaining a fixed number and toward understanding the behavior of an evolving physical field. DESI's survey operations have since been extended, running from 2026 through the end of 2028, expanding its footprint across the sky specifically so that researchers can gather enough additional data to determine, with much greater statistical confidence, whether this apparent evolution in dark energy is a genuine feature of the cosmos or an artifact of how different datasets are being combined. Confirming or ruling out this evolution stands as one of the single most consequential open questions in cosmology today, because it directly touches the ultimate fate of everything. This uncertainty about whether dark energy is constant also touches something deeply personal. In a cosmic sense, the long-term future of the universe itself. If the cosmological constant truly is fixed and unchanging, current models predict a future often called the Big Freeze, or heat death, an unimaginably long, slow process in which galaxies drift ever farther apart. Star formation gradually exhausts the available gas, and existing stars burn out over trillions of years, leaving behind a cold, dark, thinly spread universe. If dark energy is instead weakening over time, as the DESI hints suggest it might be, the long-term trajectory of the cosmos could look meaningfully different, though scientists are still working out exactly what that alternative future would entail. Either way, the fate of everything that will ever exist in this universe traces back to the exact behavior of this single elusive quantity. Cosmologists have actually mapped out several distinct possible endings for the universe, and which one we are heading toward depends almost entirely on the precise long-term behavior of dark energy, the very thing DESI and its successors are racing to pin down. If dark energy remains a true, unchanging, cosmological constant exactly as Einstein's simplest equations describe, the universe drifts toward the Big Freeze, sometimes also called heat death, an almost unbearably gradual future stretching across trillions upon trillions of years, in which galaxies beyond our own local group are eventually carried away by cosmic expansion, faster than light itself can cross the growing gulf between us, vanishing permanently beyond any possible observation. Existing stars would continue burning for a very long time, but new star formation would slowly grind to a halt as galaxies exhaust their reserves of gas, until eventually only faint, cooling stellar remnants, white dwarfs, neutron stars, and black holes would populate an ever darker, ever colder cosmos. If instead dark energy is not merely constant, but actually strengthening over time, a scenario some theoretical models allow for, one possible outcome is far more dramatic and comparatively rapid: the Big Rip. In this scenario, the accelerating expansion eventually becomes so overwhelming that it would tear apart galaxies, then solar systems, then planets, and finally atoms themselves, ripping the fundamental structure of matter apart in a finite amount of time, rather than the near-eternal slow fade of the Big Freeze. Current observational evidence does not favor this outcome, but it remains one of the mathematically possible futures, depending on precisely how the strength of dark energy evolves. Conversely, if the DESI hints of weakening dark energy are eventually confirmed and that weakening trend continues, it opens the door to scenarios cosmologists take more seriously than they once did, including the possibility that cosmic expansion could someday slow, halt, and even reverse, leading toward a big crunch, a mirror image of the Big Bang in which the universe collapses back down into an extremely hot, dense state over cosmic timescales, almost impossible to intuitively grasp. Some theorists, including the physicist Roger Penrose, have gone further still, proposing highly speculative models such as conformal cyclic cosmology, in which the extremely distant, cold future of one cosmic era becomes mathematically indistinguishable from the extremely hot, dense beginning of a subsequent one, suggesting the universe might cycle through repeated Big Bang-like events across unimaginable timescales. It's important to be clear that this particular idea remains a minority position within cosmology, lacking the kind of broad observational support enjoyed by the standard lambda CDM model, but it illustrates just how directly the fate of the entire universe And the range of theoretical possibilities physicists take seriously hinges on nailing down the true long-term behavior of this single number. Now, back to the deeper question of where a landscape of different possible values for the cosmological constant might actually come from, because this is where the anthropic argument connects to one of the most ambitious and most controversial ideas in modern physics, the multiverse. There are several distinct routes by which physicists have arrived at multiverse proposals, and it's worth being honest that they rest on very different levels of evidence. One version emerges from the theory of cosmic inflation itself. The extraordinarily rapid expansion the early universe is thought to have undergone in a fraction of a second after the Big Bang. Some models of inflation suggest that once it starts, it never fully stops everywhere, continuing eternally in some regions while ending locally in others, spinning off what are sometimes called pocket universes, each potentially settling into different values for fundamental constants, including the cosmological constant. A separate and independent line of reasoning comes from string theory, which in some of its formulations suggests an enormous number of mathematically possible vacuum states, sometimes estimated at around 10 to the power of 500 distinct configurations, each corresponding to a different possible set of physical constants, forming what theorists call the string landscape. To understand why eternal inflation produces this strange, sprawling structure, it helps to picture inflation not as a single event that happened once and then simply stopped everywhere at the same moment, but as a field with a certain energy value that can, in principle, sit at different points across space, somewhat like a landscape of hills and valleys. In regions where this inflationary field happens to roll down into a lower energy state, inflation ends locally, and a pocket universe like our own begins to form, expanding and cooling in the familiar way described by Big Bang cosmology. But in the surrounding regions where the field has not yet rolled down, inflation continues, and because inflating space expands so explosively fast, those still inflating regions grow far quicker than they end, meaning that globally, across the entire structure, inflation never fully stops. It continues forever, endlessly spinning off new pocket universes. An idea first proposed in different forms during the 1980s by physicists including Alexander Vilenka, Andrei Linde, and Paul Steinhardt, though Steinhardt would later become one of eternal inflation's more prominent critics, expressing concern that a theory capable of producing essentially any outcome somewhere within its infinite structure risks losing its predictive power altogether. If each of these pocket universes can settle into a different local value for quantities like the cosmological constant, depending on details of how inflation ended in that particular region, then a genuinely vast range of values for the vacuum energy could exist somewhere across the full structure. Even if our own observable universe only ever samples one of them, the string theory landscape arrives at a structurally similar outcome through an entirely different mathematical route. String theory proposes that the fundamental constituents of reality are not point-like particles but extremely small, vibrating strings, and that the particular way extraspatial dimensions, beyond the three we experience plus time, are curled up and compactified at scales far too small to directly observe determines the effective physical constants that would be measured within that region of spacetime, including something equivalent to a local cosmological constant, because there are enormously many mathematically consistent ways those extra dimensions could be String theorists calculate that the total number of distinct possible vacuum states could run somewhere around 10 to the power of 500, an amount so large it is difficult to compare to anything in ordinary experience. If our universe corresponds to just one of these possible configurations, selected in part by which configurations are even capable of supporting the kind of structure required for the vacuum energy question to ever be asked in the first place. The anthropic explanation gains a concrete physical mechanism to operate through, rather than remaining purely a statistical observation. If either of these frameworks turns out to accurately describe reality, then the cosmological constant would not be a single universal number requiring a unique explanation at all. It would simply be one value out of an enormous range, realized somewhere within a vast collection of regions or universes, each with its own physical constants, determined essentially by chance during its formation. Under this picture, the anthropic principle stops being merely a statement about selection bias and becomes a genuine causal explanation. We observe a life-permitting value of the cosmological constant because we could only ever have arisen in one of the comparatively rare regions where the value happened to land, in the narrow life-permitting range, out of a much larger landscape where most regions would have been sterile. It is important to be direct about the current scientific status of this idea. The multiverse, in any of its proposed forms, remains firmly in the realm of hypothesis rather than established science. It has not been observed, and by the very nature of the proposal, other pocket universes or string landscape regions may be permanently beyond the reach of any observation we could ever make, since they would lie forever outside our cosmic horizon or exist in configurations of space-time disconnected from our own. Some physicists find this lack of testability deeply troubling, arguing that an idea which cannot in principle be falsified sits uneasily within the scientific method, however elegant it might be mathematically. Other physicists respond that certain versions of inflationary multiverse models do make indirect, testable predictions about the statistical patterns we should see in the cosmic microwave background, and that ruling those specific predictions in or out through future observations would count as legitimate scientific progress on the broader question, even if we could never visit or directly detect another pocket universe itself. This tension between mathematical elegance, philosophical appeal, and strict observational testability remains one of the most active and sometimes contentious debates in the philosophy of physics. The South African cosmologist George Ellis, among others, has been particularly outspoken about where he believes the line between science and speculation should be drawn, arguing that a hypothesis which can never, even in principle, be confirmed or ruled out by any possible observation sits closer to metaphysics than to empirical science, regardless of how much serious mathematics underpins it. Proponents of multiverse thinking generally do not dispute the difficulty of direct observation, but argue that the value of a scientific idea should also be judged by its explanatory economy, how much it accounts for using how few additional assumptions, and by whether it emerges naturally from theories, like inflation and string theory, that were originally developed for entirely different reasons and happened to independently predict something resembling a multiverse as a side effect, rather than being invented specifically to explain fine-tuning after the fact. This disagreement over what should even count as legitimate scientific reasoning, when direct experimental verification is impossible even in principle, is itself one of the more fascinating undercurrents running beneath the entire fine-tuning debate, and it shows no sign of being resolved soon. There is also a quieter, more modest position that a number of working cosmologists occupy, one that avoids fully committing to either a hidden, deeper law or a vast, unobservable multiverse. This position simply holds that the fine-tuning of the cosmological constant remains an open, empirical puzzle, one that future theoretical breakthroughs, perhaps in quantum gravity, perhaps in a currently unimagined direction, may eventually resolve in a way nobody has yet proposed. Historically, Apparent fine-tuning problems in physics have sometimes dissolved entirely once a deeper layer of theory was uncovered. The strange, seemingly coincidental relationship between inertial mass and gravitational mass, something Newton simply had to assume, was eventually explained as a necessary geometric consequence within Einstein's general relativity. Physicists holding this more cautious position argue that patience, combined with better data and new theoretical tools, may eventually do the same for the cosmological constant, without requiring an appeal to either anthropic selection or an unobservable landscape of other universes. What's genuinely fascinating is how these various explanations despite their differences, converge on a shared underlying insight, our comfortable assumption that we understand what the universe fundamentally is, and why it takes the specific shape it does, may be far less complete than physics textbooks sometimes make it sound. Every candidate explanation, whether it involves a yet undiscovered deeper theory, a statistical selection effect across a vast landscape of possibilities, or some combination of mechanisms not yet even proposed, requires physics beyond anything currently confirmed by experiment. The honest state of the field is one of open, active uncertainty, populated by brilliant, competing ideas rather than a single settled answer. And that uncertainty is exactly what continues to draw new generations of physicists toward this problem. There's a version of this story that can sound almost unsettling. The idea that we live inside a universe so improbably, precisely tuned that it borders on the miraculous. But there's another way to sit with the same set of facts, one that trades unease for something closer to wonder. Whether the explanation eventually turns out to be a deeper law of physics waiting to be discovered, a statistical inevitability within some vast, mostly unobservable landscape of other universes, or something else entirely that no one has yet proposed. The honest reality is that human beings, working with mathematics, telescopes, and an enormous amount of patient observation, have managed to identify and measure this razor's edge at all. We have traced the story from Einstein first, introducing a cosmological term into his equations, through Hubble's early evidence for cosmic expansion, through Penzias and Wilson stumbling onto the afterglow of the Big Bang, through Perlmutter, Schmidt, and Riess discovering that expansion is accelerating, all the way to Desser's ongoing effort to determine whether the very constant driving that acceleration is constant at all. That is an extraordinary chain of human achievement, stretched across more than a century, converging on a single number that appears to sit at the exact threshold required for atoms, stars, chemistry, and eventually curiosity itself to exist. What scientists still don't know is, in some ways, more interesting than what they've already confirmed. They don't yet know whether the small discrepancy between theoretical predictions and observed vacuum energy will eventually be resolved by some undiscovered symmetry or mechanism within particle physics. The way past seemingly impossible discrepancies in physics have occasionally been resolved by deeper theoretical insight. They don't know whether the current hints of evolving dark energy, still sitting below the traditional threshold for a confirmed discovery, will strengthen into an unambiguous result once DESI's extended survey and other upcoming instruments, like the Vera C. Rubin Observatory's legacy survey of space and time, gather several more years of data, or whether the signal will instead fade as systematic effects between datasets are better understood and accounted for. They don't know whether the multiverse, in any of its proposed forms, reflects an actual feature of physical reality or is simply an elegant, mathematical construction that will eventually be replaced by something else entirely. Perhaps something that makes the entire fine-tuning question dissolve in a way nobody currently anticipates. What is certain is that this single, elusive number quietly built into the energy of empty space sits at the very foundation of why a universe capable of producing stars, heavy elements, planets, and observers exists at all, rather than an expanding or collapsing void containing nothing but the faint hum of quantum fields with no one present to measure them. Somewhere between now and whatever comes after the next generation of telescopes finishes mapping billions more galaxies across cosmic history, we may finally learn whether that number has always been exactly what it is, unchanging and fundamental, or whether it has been quietly shifting all along, carrying the fate of everything with it. So the question, in the end, comes back to you. Looking at a number this precise, this consequential, and this difficult to explain, do you see the signature of a deeper law of nature still waiting to be uncovered? One that will one day make the value of the cosmological constant feel as inevitable as any other fundamental constant in physics? Do you see the quiet arithmetic of an anthropic selection effect playing out across some vast landscape of possibilities we can only partially glimpse? Or do you see something else entirely, a genuinely open mystery that current physics simply has not solved yet? Whatever conclusion you lean toward, the fact that this question can even be asked, mapped, measured, and argued over with such rigor is itself one of the more remarkable things about being a small, curious part of a universe built, however it happened, precisely well enough to make that curiosity possible.